The origin of the solar system. Our cosmic address. A tiny speck in a vast universe. Look up at the night sky. What do you see? Twinkling stars, distant galaxies, a vast expanse of darkness. Our universe is incredibly enormous, filled with billions of galaxies, each with billions of stars. Our own galaxy, the Milky Way, is just one of them, a spiral of stars and gas stretching across unimaginable distances. Within the Milky Way, nestled in one of its spiral arms, lies our solar system. It's a cosmic neighborhood we call home, centered around a single star, our Sun. 8 planets, including our own Earth, orbit around the Sun, along with countless smaller objects like asteroids and comets. But how did this incredible system come to be? How did our Sun, the planets, and all the other objects in our solar system form from the chaos of space? The answer lies billions of years in the past, in a giant cloud of gas and dust. Let's journey back to the beginning, to the birth of our solar system, and explore the incredible processes that led to the formation of our cosmic home. Imagine a giant cloud of gas and dust, a nebula floating in space. This nebula, the birthplace of our solar system, was no different from many others scattered throughout the universe. It was composed mainly of hydrogen and helium, the 2 most abundant elements in the cosmos, along with traces of heavier elements forged in the hearts of long-dead stars. This cloud, though seemingly ordinary, held the seeds of something extraordinary. Around 4.6 billion years ago, something disturbed this peaceful nebula, perhaps the shockwave from a nearby supernova explosion. This disturbance caused the cloud to collapse in on itself, pulled together by its own gravity. As the cloud contracted, it began to spin faster and faster, like a figure skater pulling their arms in. This spinning motion caused the cloud to flatten into a disk, with most of the material concentrated at the center. This rotating disk, known as a protoplanetary disk, would eventually become the birthplace of our Sun and planets. The nebula hypothesis, the leading scientific explanation for the formation of our solar system, describes this process of cloud collapse, disk formation, and the subsequent birth of stars and planets. It's a story of gravity, rotation, and the gradual accumulation of matter over vast stretches of time. At the heart of the collapsing nebula, the material was becoming denser and hotter. The immense pressure and heat at the disk's center caused hydrogen atoms to slam into each other with incredible force, fusing to form helium. This nuclear fusion released a tremendous amount of energy, igniting the core and giving birth to our Sun. Our newborn Sun, a giant ball of hot, glowing gas, dominated the center of the protoplanetary disk. Its powerful gravity continued to draw in material, growing larger and hotter over millions of years. As the Sun blazed at the center, the remaining gas and dust in the disk began to cool and clump together. The birth of the Sun marked a turning point in the evolution of our solar system. Its intense radiation and solar wind, a stream of charged particles, pushed the remaining gas and dust outward, shaping the protoplanetary disk and influencing the formation of the planets. From the remnants of this swirling disk, a cosmic ballet of planet formation was about to begin. In the colder outer regions of the protoplanetary disk, dust grains, chunks of rock and ice began to stick together. This process, called accretion, started small, with tiny particles colliding and sticking together due to electrostatic forces. Over millions of years, these clumps grew, forming planetesimals, objects ranging in size from meters to kilometers. These planetesimals, drawn together by their mutual gravity, continued to collide and merge, gradually forming larger and larger objects. Closer to the Sun, where temperatures were higher, only rocky materials could condense and survive the intense heat. This led to the formation of the inner rocky planets: Mercury, Venus, Earth, and Mars. Farther out, beyond what is called the frost line, temperatures were cold enough for ices, such as water ice, methane ice, and ammonia ice, to solidify. These ices, along with rock and metal, provided the building blocks for the gas giants: Jupiter, Saturn, Uranus, and Neptune. Giants and dwarfs, the diversity of our planetary family. Our solar system is a diverse place, with a fascinating array of planets, each with its own unique characteristics. The inner rocky planets are relatively small and dense, with solid surfaces and thin atmospheres. Mercury, the smallest planet, is a scorching world, while Venus is a greenhouse planet shrouded in thick clouds. Earth, our home planet, is unique for its liquid water oceans and abundant life. Mars, the red planet, is a cold, dry world with evidence of a wetter past. The outer solar system is dominated by the gas giants, massive planets composed mainly of hydrogen and helium. Jupiter, the largest planet in our solar system, is a swirling giant with a powerful magnetic field. Saturn is renowned for its stunning ring system, made up of countless particles of ice and rock. Uranus and Neptune, the ice giants, are blue-green worlds with frigid atmospheres composed of methane, water, and ammonia. Beyond the gas giants lies the Kuiper belt, a region populated by icy bodies, remnants from the early solar system. Pluto, once considered the 9th planet, is now recognized as a dwarf planet, one of many icy worlds residing in this distant realm. Rocky remnants, asteroids, the leftovers of planet formation. Scattered throughout our solar system are billions of asteroids, rocky remnants from the early days of planet formation. These cosmic wanderers come in various shapes and sizes, from small pebbles to dwarf planets hundreds of kilometers in diameter. Most asteroids reside in the asteroid belt, a vast region located between the orbits of Mars and Jupiter. These asteroids are believed to be leftover planetesimals, prevented from forming a planet by the gravitational influence of Jupiter. While most asteroids reside in the asteroid belt, some have orbits that bring them close to Earth, known as near-Earth asteroids. These space rocks pose a potential threat to our planet, and scientists are actively tracking their movements to identify any potential impact risks. Icy wanderers, comets, and the Kuiper belt. Beyond the orbit of Neptune lies the Kuiper belt, a frigid region populated by icy bodies, remnants from the early solar system. These icy objects composed of frozen water, methane, ammonia, and other volatiles are believed to be leftover building blocks from the formation of the giant planets. Comets, often called dirty snowballs, originate in the Kuiper belt and beyond. As a comet approaches the sun, its icy surface begins to vaporize, creating a glowing coma, a cloud of gas and dust, and a long streaming tail. Comets are fascinating objects offering glimpses into the composition of the early solar system. Pluto, once considered the 9th planet, is now recognized as a dwarf planet and a prominent member of the Kuiper belt. Its discovery in 1930 expanded our understanding of the outer solar system and the diversity of objects orbiting our sun. Beyond the solar system, exoplanets and the search for life. For centuries, our understanding of planetary systems was limited to our own solar system. However, in recent decades, astronomers have discovered thousands of planets orbiting other stars, known as exoplanets. These exoplanetary systems come in an astounding variety, showcasing the incredible diversity of planetary systems in the universe. Some exoplanets are gas giants orbiting incredibly close to their stars, while others are rocky worlds located within the habitable zone, the region around a star where conditions might be right for liquid water to exist on a planet's surface. The discovery of exoplanets has revolutionized our understanding of planet formation and the potential for life beyond our solar system. Scientists are now eager to study these distant worlds in more detail, searching for signs of atmospheres, oceans, and perhaps even evidence of extraterrestrial life. A cosmic perspective. Understanding our place in the universe. Studying the origin and evolution of our solar system provides us with a profound cosmic perspective. It reminds us that we are part of something much greater than ourselves, a vast and ancient universe teeming with stars, planets, and endless possibilities. Understanding how our solar system formed helps us appreciate the delicate balance of conditions that allowed life to arise on Earth. It also allows us to compare our planetary system to the thousands of exoplanetary systems discovered in recent years, providing insights into the diversity and evolution of planetary systems throughout the universe. Unraveling the mysteries. The importance of studying our origins. Studying the origin of our solar system is not just an academic exercise. It has profound implications for our understanding of the universe and our place in it. By unraveling the mysteries of our cosmic past, we gain insights into the processes that govern the formation of stars, planets, and the very elements that make up our bodies. Understanding the conditions that led to the formation of our solar system can aid us in the search for life beyond Earth. By studying the chemical composition of comets, asteroids, and other celestial objects, we can learn more about the building blocks of life and the potential for life to arise elsewhere in the universe. The future of exploration, new horizons and beyond. Our exploration of the solar system is far from over. Spacecraft like NASA's New Horizons, which flew past Pluto in 2015, continue to reveal the secrets of the Kuiper Belt and beyond. Future missions are planned to study asteroids, comets, and the icy moons of the outer planets, searching for signs of past or present life and unraveling the mysteries of our cosmic neighborhood. The quest to understand our solar system is a journey of discovery, driven by our innate curiosity and our desire to explore the unknown. As we continue to probe the depths of space, we can be sure that new discoveries await, expanding our knowledge and inspiring future generations of scientists and explorers.